Thank you. Hello, everybody. I'm David Sneider. I'm one of the co-founders of Lit Protocol. Thank you for being here. And we've got 10 minutes together, and we're going to try to cover a lot of information. But yeah, let's get underway. So here's what we're going to talk about today. First things first, what is Lit Protocol? And then we'll talk about encryption and how that relates to the work at Ceramic and Tableland. And then finally, onboarding and wallet provisioning and some of the work happening there, which of course is the prerequisite to being able to own your own data, is being able to have access to a key. So Lit is a distributed key management network. If you think about fundamentally what makes digital ownership possible applied to both user-owned data as well as digital assets, it's fundamentally two things. And this is very clear if you look at the founding document of our space, the Bitcoin white paper. The second sentence says, digital signatures provide part of the solution, and we also need a way to prevent double spend issue. And then the rest of the 9 pages are about proof of work. And so the security model here, we won't spend too much on this, is to use something called multi-party computation threshold secret schemes to divide keys up into parts. And then each of the nodes that is managing one of these key shares is running inside of a trusted execution environment. We use something called a TEE. And inside of that TEE, there's a JavaScript execution environment, so developers can articulate any program, any logic that they want to dictate how that distributed key is going to sign or decrypt things. This is a generalizable primitive around decentralized signing and encryption. Everything you see on this list, there's one or more venture-backed teams building across these categories. I don't have the logos, but the way that you use this, all of the cryptography gets abstracted away from a developer who's building with the system. As you can see, single functions for signing a transaction, encrypting content. And so the next portion, we'll talk a little bit about how does the encryption work, and then we'll finish with signing. So you can see here is like the step-by-step method, but functionally what is happening here is if a user has some data, let's say it is an image, Alice encrypts that image to the lit public key and then sets a rule. An example of a rule can be you have to own 10 ETH in order to decrypt that image. Bob owns 10 ETH. He shows up later. He makes a concurrent connection to all of the lit nodes and says, hey, I'm Bob. I own 10 ETH. I can prove this based on my signature. The lit nodes are independently validating that Bob meets that rule. And then kind of in the same mental model of how like torrents work, each of those nodes is then sending Bob down an authorization. And when Bob collects enough of those authorizations, which is the threshold in threshold secret system, in the case of the lit network, it's 2/3 of the network, Bob can then decrypt that content. So we have client-side encryption and client-side decryption. And so these access control rules can be stored anywhere. They can be stored on Ethereum. You can see in this example, we've got a contract that you have to own greater than 0 and able to be enabled to decrypt. You can use any custom contract on Ethereum. So here's the Moloch DAO contract, which creates the construct of a share inside of that contract. And the decryption condition is based on owning shares. The same is true for Solana. The same is true for anything on Cosmos. And also anywhere on the web broadly. So here's an example where decryption is enabled based on the temperature in a given city. This can also apply to access control rules stored on the DID doc in places like Ceramic. So it's really extendable. The whole intent here is to make this a highly generalized system around rules-based decryption. And there's some other kind of interesting ways to make this work for a variety of use cases, including adding Boolean logic and or operators to building out this decryption rule set, as well as being able to do time lock. And so I'll just walk through a couple use cases of how this technology for conditional encryption and decryption is being used today. Fox Corporation recently launched a project called Verify. It's basically an open web protocol. It uses IPFS and Polygon and Lit, where any journalist can, rather than syndicating their content to other media companies, they can essentially publish their content on this open system, it is encrypted, and then either another media company or like an LLM bot can purchase a license to decrypt that content and serve it up to their reader, their end user. And this, again, I just want to clarify, all these examples I'm going to show you are all following the same structure that we talked about earlier, which is the party encrypts and sets a rule, another party meets that rule and then can decrypt that content. Silk is using this for backup and recovery of key material for users. Streamer is using this in the context of data marketplaces, not too dissimilar to the Fox example, but in a more generalized context. Lens Protocol does this for gated publications with Lit, where you have to follow somebody on Lens in order to decrypt the content, essentially at parity with something like Patreon that we would find on Web 2. Token gated content, you could call this. There's been some amazing work in the world of user-owned data around encrypted verifiable credentials by like Awamo, Terminal 3, where a user can essentially in their data backpack stored, in this case on Ceramic, that data is encrypted with Lit, and then that user has the power of selective disclosure, which are these access control rules to dictate who can read that information, provided that they meet those conditions. And then this one's pretty funny. Another example of this is digital product NFTs. Michael Jackson's first album ever was encrypted with Lit in the form of a digital product NFT. This thing is doing pretty well on the secondary market. So keys, like asymmetric cryptography, public-private key pairs functionally have two core features: encrypting stuff like we just talked about, or like in the example of Signal app, a private messenger. The other side of keys, if you will, is signing. And so what we're going to talk about in the next couple minutes is how do we get keys to people in the most coherent way? How do we solve some of the challenges around Web3 UX, which applies to both user-owned data as well as to user-owned assets? So the prerequisite understanding here is like, what is a crypto domain? You probably all have a familiarity with .eth, ENS. There's a couple of vendors here. Essentially what it is, it's an on-chain registry connecting a human-readable string of letters to a crypto domain. And in that NFT, there is some metadata where you can say, here is something else about that domain. And so the big insight is to take the crypto domain and combine it with a non-custodial key, like the types of keys managed by Lit, in order to essentially create what we've been thinking as like the ultimate Web3 account object, where a user can have a flow around being able to log in with a name inside of any dApp, again, whether for user-owned data or digital asset purposes. And essentially upon clicking that button, this is what the user sees. They type in their name. I'll show you in the next slide about how this works. Then they do their multi-factor authentication. The signature is generated. They're logged into the dApp. We think this kind of like turns the crypto domain by combining it with a wallet into something that is the 10x better than an email identifier for an individual. How this works underneath the hood is that in that metadata associated with the crypto domain, it's really quite simple. All we're doing there is writing the name of a key management vendor, whether it's something like Lit or Fireblocks or Coinbase, such that when the user types in that name, alice.eth, the login modal looks up on chain and goes, where is the key associated with this name? The key management provider gets pinged. It goes, oh, they're using Lit in this context. Then the Lit authentication flow starts. Alice signs in with Google, enters her 6-digit authenticator code. The signature is generated, and she's logged into the application. And the state of this today is we have a working demo that is through the context of a WAGMI custom connector. We've been coordinating with the team around EIP 7555, which is working on single sign-on, and we'll be publishing CAPE, a chain agnostic improvement proposal for this method next week. It's something that we're really excited about. If this login with name thing is interesting to you and we're doing it as an open standard, would love to figure out how we can collaborate in some way. And so I think we're getting close to 10 minutes, but I just want to end here, which is over the past 3 years of doing R&D to get this network live, I'd say a fundamental perspective shift that we've had around like blockchains and what is happening here. What is this revolution? We've really been thinking about it in the context of the revolution is actually the digital signature revolution. Blockchains are like where the attention is at in terms of the new technology enabled by digital signatures. But what we're actually doing is like a back-end revolution for society in terms of upgrading things to cryptographic systems, to signature-based systems. And just think that it's really promising and wanted to share that view. And yeah, the work that we're doing is around creating a generalizable network layer for decentralized signing and encryption for a variety of different application types, as you can see. And with that, here's how you can find us. And yeah, I really appreciate the time, and I'll be around if you want to talk more. Thanks so much.